Okay, hello guys. So now that we have basically seen what one-dimensional movement will be and the equations that will help us solve one-dimensional movement, then let's go ahead and start actually doing an exercise. Okay, let me just connect my computer so that, okay, wait, there we go. Okay, there we go. So let me try this out. Can we write? Okay, yes, I can write. Put another color and we can start. Okay, so this exercise will be about free fall. Okay, so this exercise will be about free fall. So basically, free fall is when you let an object go from a certain height and it falls freely. So let's picture that we have the Leaning Tower of Pisa. So grass is right here. We have grass. And I'm gonna get artistic, by the way. So uh, let's see, have something like that, and then something like that, and then something like this, and the different levels, and different columns. Oh, let me erase all of them. Just put columns like this. Okay, so that is the Leaning Tower of Pisa, right? So we're gonna situate ourselves here at the top. So we are here. And we're going to let go of a ball and we're going to let it fall down in this direction. Okay? And we'll figure out how much what position the ball has at different time intervals, so at time intervals. And we will also figure out the velocity of the ball at different time intervals as well. And finally, we can figure out what is the time required for the ball to actually hit the ground. So to reach the ground. To reach the ground. Okay, so one important thing about this is that people, I'm working. Yeah, my dog wants attention. You'll hear him whine. I'm sorry. So this thing has a height of 57 meters. 57 meters. Okay, so our first approach to solving this problem, we know that it's a free fall problem. Okay, we know that this thing is free fall. And we already figured out the equations that we can use for free fall. I think I have them here. There we go. These are my equations for free fall. I'm going to be using equations 1 and equations 2. Why? Because the problem asks for the velocity at different time intervals, and it also asks for the position at different time intervals. So we only need to use these two equations for now. Okay, so let's return to the problem. Okay, so the actual problem asks to find the position. So find the position and velocity of my ball, the ball at time equals 1 second after I drop it, time equals 2 seconds after I drop it, and time equals 3 seconds after I drop it. Okay, so first thing first that you need to do when you're working with these type of problems is the first thing to do, so first step and this is very, very, very important. The first step is to define my reference frame. Reference. Because remember, these equations, whether they give us a positive sign or a negative sign, those will only have meaning with respect to our reference frame. Okay, so in this example, I will say that up is positive and down is negative. Okay, correct? And this is the most important part right now, is that I will place at this point right here where the original ball is, this will be my position, my original position, y0, and I will call this, okay, so I could either say that this is 57 meters above my ground, and that would be taking my ground as my original position, but I'm going to mix it up a little bit, and I'm going to say that here at this point where the ball is where my position is, my original position is 0. Okay, so at this point, this is my position 0. If the ball goes away from this point, my position would be a positive number. If the ball goes in this direction away from my 0, the ball would be in a negative, will have a negative number. The position would have a negative number. Why? Because this is my reference frame. Okay, this is what I am, at this level, I am establishing my 0. I am not establishing my 0 here at the ground level. I am establishing my 0 here at the top level. Okay? So now we have enough information to actually start working on the problem. Oh, one other thing that is very important is that since I am working on Earth, my acceleration is 9.81 meters per second squared. But we know that acceleration is a vector quantity, correct? Acceleration is a vector. Therefore, it must have both a magnitude and a direction. What sign does this magnitude need to have in order to consider the direction? Well, we look at our reference frame. We know that going up is a positive number and going down is a negative number. Therefore, as acceleration is always downwards, no matter this convention, we will say that it's negative. Okay, that way we know that the acceleration that this thing will suffer is in this direction. Okay, this direction right here. Another important thing to manage is that the problem never states that I throw the ball either up or down. Therefore, my original velocity in the y direction is 0. Okay? If I were to throw the ball upwards, then VOY, my initial velocity, would be a positive number. If I were to throw my ball downwards, my initial velocity would be a negative number, right? Because of my convention, what I'm saying right here. But since the problem does not state that my ball is either thrown up or thrown down, the problem only states that I let go of the ball. Therefore, my initial velocity is 0. So this thing right here does not apply. So not applicable. I don't know if it's with a two double P. So applicable. I think it is. Okay. So now we have everything we need in order to actually do the problem. Okay. So now what I'm going to do is let's start working with the equations. Okay, so in order to do that, here I have another applet running in the background, so this is it. Okay, so these are my two equations. We already saw them in the last video called vertical throw equations or something. So this is equation 2 and equation 1. These two equations are relating my position with respect to to time, and this one is relating my final velocity with respect to my initial velocity, my acceleration, and time as well. So the problem is asking me to find the position and velocity of the ball at 1 second after I let go of the ball, at 2 seconds after I let go of the ball, and at 3 seconds after I let go of the ball. So let's do first the 1 second one. So to find the position, so let's call this find position of ball at time 1 second after it is after we let go of it. So this y is the position of the ball, and we already have the formula that is going to tell us the position of the ball with respect to time, and that is what we want. So it's a direct substitution, so 1/2 of my acceleration. But my acceleration, I already know that it's minus 9.81 meters per second squared times the time. Okay? But we already know that time is equal to 1 second. So 1 second, and this should be squared. Oh, so 1 second. Oh, sorry. 1 second squared. So this is 1/2 acceleration times time squared plus the initial velocity. Remember, I did not say that I'm throwing the ball either upwards or downwards. I'm just saying that we let go of the ball. Therefore, my initial velocity is 0 times the time, which is 1 second, plus my initial position, y0. So let's look at the initial position right here before we continue. Look, the initial position is at y0 equals 0. Why? Because I am stating that this is my reference plane. This is my reference frame. From here, I will be measuring positions. Okay? So even though I am 57 meters above ground, I don't care about that. I'm just saying that at this level, this is my y0. Okay? This is my reference. This is my reference right here. Therefore, oh, I don't know how I did that. Okay. Therefore, my initial position is also 0. If you do the math, this is equal to minus 4.9. What units? Well, if this is meters per second squared and this is seconds squared, this is meters. So let's look at the sign right here. It says minus 4.9. At the beginning, that might not make so much sense. But now let's look at the graph again. Let's look at our figure again. We're saying that after 1 second, my position is negative 4.9. So that means that it travels in this direction. So originally, my ball, here, let me put this in white. My ball was here at y equals 0. And now, after 1 second, my ball is here. And what is the distance from here, from my reference frame, to this point is minus 4.9 meters. Okay, so from this point to this point after 1 second, so this is t equals 1 second. So after 1 second of free fall, my ball changed from this position to this position, and this position is minus 4.9. All of these calculations are referenced to my reference frame. So they are referenced to this point right here. Okay, so now let's calculate velocity. Velocity is calculated with this equation. Vy, which is my final velocity, is equal to my initial velocity, which is 0, plus negative 9.81 meters per second squared times the time squared. The time is 1 second, and that is squared. So let me put this like this. 1 second squared. Therefore, 0 plus negative 9.81 times 1 is negative 9.81 meters per second. Why meters per second? Oh wait, no, I think no, this shouldn't be squared right here. Yep, there we go. Let me double check that, because here. Yeah, look at it. It shouldn't be squared. It shouldn't be squared at all. My mistake. I am sorry. But now we're okay. So this is VOY my original velocity plus my acceleration times the time. So if I multiply meters per second squared times second, I get meters over second. That's it. So that means that at this point in time, my projectile or the ball has a velocity. So the velocity will be represented. Put it in red. So at this point, the velocity of this projectile is minus 9.81 meters over second, or meters per second. Okay, so now I took the liberty to actually calculate it for 2 and 3 seconds using Microsoft Excel. Okay, so I just used the formula here. So I put y position and velocity. I'm stating that my original position is at 0, my original velocity is at 0, and my acceleration is minus 9.81. As you can see here in the formulas, this thing is I'm using the same formulas that I just showed you, but I'm just telling Excel to do it for me. That way I can make it do more calculations instead of just putting it manually in the calculator, right? So look, at 1 second, it checks out with what we just calculated. At 1 second, my y position is at negative 4.9, and my velocity is at negative 9.81. Negative is indicating that the velocity is going downwards. Now, I calculated it for 2 seconds. At 2 seconds, my projectile is at negative 19.6. So let's whoops, okay. So at 2 seconds, it traveled from from 0 to negative, so let's see, somewhere around here. So now it's not here anymore. Now at time equals 2 seconds, the projectile moved from this position right here all the way to this position right here. And this is minus 19 meters, 19 point something. Okay, this thing again is referenced not to this point, so the distance, so negative 19 is not from here to here, but from here to my 0. Okay, I moved 19 meters away from my 0 at 2 seconds. And the velocity that my projectile has is 19.62 as well. Okay, so let me put this here. So now the velocity this projectile has is negative 19.6. And it makes sense, right? Because we're being accelerated downwards, okay? That is the only force that is working here. This is meters per second. And finally, at 3 seconds, I am at negative 44 meters. So once 3 seconds have passed, my ball is almost at the bottom. This is t equals 3 seconds. And now I am basically, okay, I'll put it here. Whoops. Okay, there we go. So right here I am at negative, what was the number? I forgot. Negative 44. Okay, so the distance from this ball to my original position is negative 44 meters. You see, I have already traveled 44 of the 57 meters, right? So at 3 seconds, my ball hasn't hit the ground yet, but it's getting pretty close. At this point, the velocity has also increased, right? Now the velocity at t equals 3 seconds is negative 29. So negative 29 meters per second, right? The velocity is incrementing in this direction. Why? Because the acceleration is going in this direction. And remember, acceleration is the increment of velocity. Therefore, if its velocity is changing in this direction, then it must mean that we are accelerating in that direction. And you know that is true because this is gravity. Okay? So that is it. That is basically it for the problem. We have already calculated the position with reference to my original point, to where my 0 was. We have calculated the position, and we have calculated the velocity. Now what I did here is I took this formula right here, this one, and this formula right here, but now I calculated my position and my velocity not at 3 points, not at 1, 2, and 3, but at all of these points from 0 to 4 at 0.2 seconds of an interval. So 0.2 seconds after I let go of my ball, this is the position of the ball, this is the velocity. At 1 second after I let go of my ball, this is the position, this is the velocity, etc., etc. All of these values were obtained using, using these two formulas, correct? Okay, and actually they might be wrong because I probably used, yep. Oh no, they're fine, they're fine. Yeah, they're fine. Okay, so this is the position and this is the velocity of the ball at this time. What I did next was to create a scatter plot. Okay, so this scatter plot is giving me the position of the ball. Remember, the vertical position of the ball with respect to time. Okay, so now what I'm doing is at 0 seconds, my ball is at 0, so it's at the very top. At 0.2 seconds, so here, my ball is practically at the top, right? It has only moved 20 centimeters away from me. It has only dropped 20 centimeters. At 1 second, it has already dropped 4.9 meters. So at 1 second, it has dropped 4.9 meters, and so on and so forth. So if the height of the tower is around 57 meters, wait, let me double check that. Yeah, 57 meters. So at what time does the ball hit the ground? Well, we can analyze this graphically, right? Because we can figure out that the ball has hit the ground once this value is negative 57. So look right here, between 3.4 seconds and 3.6 seconds, we see that the ball passed from negative 56.7 to negative 63. So that means that at 3.4 seconds, the ball is just about to hit the ground, and at 3.6 seconds, this is indicating that the ball, if there was no ground, would have already passed the 57-meter mark. So we can estimate that my ball will take around between 3.4 and 3.6 seconds. So why don't we add another point here? Okay, so let's calculate. It's calculated with 3.5. I just need to drag this formula right here and drag this formula right here. So look, at 3.5 seconds, my ball is at negative 60 meters. Okay, we are looking for the time between that it will give us a position of negative 57 because that's the height of the tower. At 3.5 seconds, we have traveled at negative 60. We have traveled 60 meters, which is more than the height of the tower. Right? So we can say that the time it takes for the ball to travel from my hand to the ground if I drop it from the Eiffel Tower should be around 3.40 something seconds. 3.40 something seconds. Okay? How can we calculate it? How can we calculate this mathematically? Well, we can use this equation. Okay? So, now we know what is the total height, the final distance, the final position of the ball. This final position would be negative 57 meters, right? This is equal to, I'm using equation number 1. This is equal to 1 half of my acceleration, which is negative 9.81 meters per second squared, times, we don't know the time here, okay? This is our unknown, because we don't know how much time it's going to take from the ball to drop from my 0 position with 0 velocity and to get to the negative 57 mark. So we are actually trying to figure out the time. So I can say time squared plus VO, my initial velocity, which is 0, So this makes the equation very simple, times v0, which is 0, times t, plus my original position, which is 0, again, making my equation even more simple. So these two things, they disappear, so we get minus 57 equals 1 half, I'll just put it at 0.5, times negative 9.81 meters per second squared times the time squared, right? So times the time squared. So if we have time by itself, we know that time squared, let me put this as this, time squared is equal to negative 57 divided by 0.5 times negative 9.81. So time squared, okay, time squared is equal to, here, I don't have a calculator around here. So, okay, let's just use the computer's calculator. So, where's the calculator? Yeah, I'm sorry, I'm not a Mac user, so, okay, there we go. So, 57 divided by 9.81 times 0.5 is 4.905. So this is around 11. Shit. Sorry. Let me do that again. 57 divided by 4.905 is equal to 11.62. 11.62. And if we take the square root of that, so how do we do that with this type of calculator? Wait, file, view, scientific, okay. So we take the square root of that, 3.408. So 3.408. So technically it's around, using three significant figures, would be 3.41. Okay, so that is exactly what we looked here with it in our Excel. We figured that my velocity would be, my time would be between 3.4 and 3.5. Look, 3.4 it's at minus 56 and 3.5 is at minus 60. So let's try 3.41, and let's see our velocity and position. Okay, so if we take, let's take only three significant figures. Oh, one more. Okay. So at 3.41, look, I am exactly at negative 57. So I figured out that with my graph, I figured out what was the time that it took the ball to fall from my hand and hit the ground, but I can also calculate it. And we did that right here using my equations. Okay, so I'll stop the video right now. My next video will be doing the exact same example, but now my reference frame will not be up here, but it will be down here, and we'll calculate it the same way. But for now, this is enough. So thank you for watching, and see you on the next video.